Well, greetings everyone. Welcome to this special presentation about the Northern Lights. My name is Mike Murray. I'm the astronomer and manager of the Delta College Planetarium in Bay City, Michigan. And we're glad to have so many of you with us. You are welcome to leave comments, questions in the comment section. But with the number of people joining us today, we may not be able to answer them all, but feel free to leave some in there so we can have a look. And our moderator, Brian Kennedy with our planetarium will help us with that. We do ask that you please do guard your privacy here and in the comments section especially. Please don't be clicking on any links in there. And so with that out of the way, let's go ahead and get started. The Northern Lights, or Aurora Borealis as Galileo called them, have fascinated people for millennia. In this program, we're going to explore their folklore, causes, and effects. And in fact, what you're seeing here is a time-lapse sequence from Tromsø, Norway. Located some 69 degrees north latitude, this is one of the prime locations to see the aurora because you're almost directly underneath what's called the auroral oval. And so what is that? Well, this is a part of what our program is all about because we're going to give you tips on how, when, and where to observe the aurora. And that will include some live webcams for the many of us who don't live at those particular latitudes. The Northern Lights have driven folklore and influenced history, religion, and art, as you could probably well imagine. Probably the earliest known depiction of the aurora goes back 30,000 years in this Cro-Magnon cave painting in Europe. They feature prominently in Norse mythology, where they were believed to be reflections of the shields of the Valkyries, racing across the sky on their way to their resting place in Valhalla. A particularly strong display was seen all across Europe in 1570, depicted here as candles above the clouds by an artist in Bohemia, an area now known as the Czech Republic. One of my favorites is in Finnish mythology, where it's believed that the Aurora Borealis is caused by a firefox who ran so quickly across the snow that its tail caused sparks to fly into the night sky, creating the aurora. In fact, the Finnish word revanchelet literally translates as foxfires. In 1619, Galileo coined the term Aurora Borealis after Aurora, the Roman goddess of morning. He had the misconception that the auroras were due to sunlight reflecting from the atmosphere. But the English scientist Henry Cavendish made the first quantifiable observations of the aurora in 1790. He used triangulation to estimate that the aurora light is produced about 60 to 70 miles up, a lot higher than many had originally thought. The oldest known photograph of the Northern Lights was taken on February 1st, 1892 in Norway. Given the difficulty making sensitive film emulsions of the time, this was actually pretty good. Now, if you look here, you can see a hint of some rays and spikes running through the picture. And that's pretty hard to get in those days. In 1902, it was Christian Birkeland, a Norwegian physicist, who concluded from his Torella vacuum chamber experiment that auroral light was caused by currents flowing through the gases of the upper atmosphere. This is exactly how our modern-day neon lights work. But we still have the question, what is it that triggers the aurora? It was in the 19th century that scientists began to notice a connection between the storms on the sun and the appearances of aurora. The sun has sunspots that go through an 11-year cycle. These are magnetic disturbances on the surface of the sun, where the solar plasma follows magnetic loops that poke out of the surface. But sometimes those magnetic field lines can snap, and when they do, violent eruptions can release vast amounts of charged particles out into space at nearly 5 million miles per hour. Well, it just so happens that we're heading into the start of a new sunspot cycle. The next maximum is projected to hit in 2025, but sunspot numbers are already beginning to increase, and that means auroral activity is beginning to increase as well. So how does that cause the aurora? Well, two things. The Earth has both a magnetic field and an atmosphere. Our magnetic field is produced deep in the Earth's interior. The outer core is liquid iron and nickel. This convective movement, or its convective movement, against the solid inner core acts like a generator, creating a magnetic field that surrounds our planet. It's one of the main reasons Earth can support life, because it blocks out much of the harmful radiation coming in from space. Notice here how the magnetic poles are offset from the rotational poles. They're not lined up perfectly. The charged particles of a solar storm are carried by the solar wind, and when they reach Earth, they get trapped in our magnetic field. Now, some of them are deflected around the Earth, but others are funneled into the polar cusp, where they are directed toward the north and south magnetic poles. There are the cusps surrounding the geomagnetic poles. Well, as they come rushing down into the atmosphere, they collide with atoms of oxygen and nitrogen, causing them to fluoresce like a light bulb. And that means, voila, the Aurora Borealis for those of us in the high northern latitudes, or the Aurora Australis for those in the southern hemisphere at extreme southerly latitudes. It might look as though the hotspots for aurora are right near the north and south poles, but they actually come through a ring surrounding the geomagnetic poles. We call this the auroral oval. This is the best spot to observe them, and that's generally between 60 and 70 degrees north latitude for the northern hemisphere. So what regions are we talking about? For the northern hemisphere, that's Canada, Yukon territories, Alaska, northern Siberia, northern Scandinavia, southern Greenland, and look, all of Iceland. This is the region that you'll be able to see auroras 80 to 100% of the time, when it's dark, that is, and of course when there's no clouds. For the southern hemisphere, it cuts across Antarctica with a large portion at sea. Do you see where the South Pole is? Notice that the auroral oval is not centered right on the South Pole. Well, remember we said that the geomagnetic poles are offset, which means if the South Pole here is our rotational pole, the magnetic South Pole is way over here on this side of Antarctica. And that's why the auroral oval is aligned the way that it is. The offset is about 10 degrees, and so that's quite a bit in terms of how much of the surface.
So, Mike, I have a couple questions from the chat here. One question is, what is the furthest south documented seeing of the Aurora Borealis that we've seen in the United States, if you know that? And there's another question about if the colors that people observe in the aurora are different depending if they're looking at the northern or southern lights.
They're not, and actually you guys are jumping ahead on me, which are great, awesome questions. That's exactly why I've got them in specific sections of the presentation. But yes, very good. This chart right here, I know it's going to be it's kind of hard to read some of the words, and don't worry about that. The point here is that there are scales of different levels of magnetic storms, the geomagnetic storms, triggered by the solar storms. And depending on how high the storms go, the number here is the KP index. And the higher the number is, the more violent the geomagnetic storm, and that means the lower, the farther they will reach. So for those of us in the United States, if we were to get a KP9, which is incredibly rare, those might happen maybe once every 20 years or so, those could stretch all the way into the southern United States. And I've got some great charts here to show you. So again, according to that index, if you were just the normal background rate, no real storms going on, just the background solar wind, then being here underneath the auroral oval would be ideal. But as a geomagnetic storm kicks off because of a solar eruption, then you might see the auroral ring or oval stretch further and further south. A rare KP9 event actually took place in 1989, and that produced aurora all the way down in Florida. And that's, I think, the last time they were seen there. And I know that they were visible because I was living there at the time, and I saw them, and believe me, people were freaking out. It made front page news all over the state. So these G's and KPs, don't worry about those. That's just really basically telling you the level of either storm and the intensity of the geomagnetic interference or disruption going on in the atmosphere. So let's turn that around and look at Europe so you can see how far the aurora can reach south during intense storm events. Generally, as we noted, you want to be somewhere way up near that 60 to 70 degrees underneath the auroral oval, where you'll usually be able to see some activity if it's clear and dark. And it really takes a good storm to get way down into Europe. A prediction is, by the way, I need to point out, they are notoriously unpredictable as far as the northern lights go. A prediction that comes out is not a guarantee because there are so many changing variables in the geomagnetic storm and the atmosphere. Also, it's better to look at what are called predictions rather than alerts. Many times alerts come out with a delay. And so if you wait to get one, chances are the storm may have already passed. Okay, so do look for aurora predictions. And I've got some sites I'm going to share with you here pretty quick. So we don't want to leave the southern hemisphere out. What about some of the geomagnetic levels, the storm levels in the southern hemisphere? Well, as you can see, most of it is over Antarctica, but when there is an exceptionally strong storm, it might reach as far up as King George Island or even the southern tip of South America. For the other hemisphere, they can occasionally reach New Zealand, Tasmania, and southern Australia. And again, sometimes farther. Just because this is the location where the storm has reached, you can actually count maybe another few hundred miles because you'll be able to see it really, really low on the horizon as you get further away from the red level ring. Geomagnetic storms can be mapped according to a color scale, and I like this one because it shows you just how far they can spread. Here you can see the effects of a light to moderate storm. Notice how far south it's stretching. With a major activity, a major storm here marked in red. Notice how much farther the storm is reaching south, down into the northern stretches of the United States. So if you happen to be in one of these zones during a geomagnetic storm, what can you expect to see? Most often, the aurora will begin as a very subtle glow on the horizon. Many people may have actually seen them but didn't realize they were aurora because it just looks like the glow. Maybe it resembles the glow of a far-off town. You might not even notice any color at first, but if you do, it will most likely be pale green in shade. Over time, you need to watch for gradual changes. In particular, look to see if the glow seems to lift off the horizon into a strip that's roughly parallel to the ground. In other words, you'll know it's the aurora if it appears above the horizon with a sharp border at its base. That's how they might start. From there, the display may or may not erupt higher into the sky. If it does, there are some features to look for. This one here, for example, is considered a curtain aurora for the curved and curtain and vertical extensions. What you do is, if you do happen to see these, watch for slow and subtle changes in brightness and shape. I want you to keep in mind too that these are time exposure photographs. To the naked eye, they won't appear this bright and the color will be kind of muted, but strong level storms will make them more obvious. This is one of my favorite examples of a curtain aurora. I think you can see why they're named that way. There can be spikes that will grow and fade, sometimes with different colors, or a similar display called rays. The nice thing about being right under the auroral oval, or further south if there's a strong display, is that the northern lights can appear higher up in the sky. They might produce what are called coronal displays, meaning right out of the zenith, the top of the sky. In cases of intense storms, the aurora can cover the entire sky, all the way to the southern horizon, and display shimmering. Now, this is sped up somewhat because it's taken from a series of time exposure photographs, but you can see that that kind of shimmers, and sometimes they'll seem to emanate from the top and shimmer all the way down to the horizon. I saw this in Montana back in the late 90s, and it was amazing just to see. It almost felt like or looked like a pulse that was just moving all the way down from the zenith. All right, so somebody was asking about colors. We mentioned that the most commonly observed color in the aurora is green, but you can occasionally see others. Colors in the aurora depend on the speed of the charged particles coming in, the atoms they strike, and at what altitude. The highest occur at about 150 miles up. That's where the reds, and they're kind of rare. The reds occur only when there is a really strong storm of particles hitting the Earth. They occur above 150 miles, and up there, the oxygen is less concentrated and is excited at higher energies than the denser oxygen that's lower down. It's this area right in the middle, between about 60 and 120 miles up, that we see the most predominant green color. Now that's also from oxygen, but there are much higher concentrations there. And sometimes there are also secondary excitations of the molecules. But in any case, coupled with the eye's greater ability to detect green color, this makes it the most predominant and frequent auroral color that you're going to see. Below 60 miles is where you'll occasionally see blue and purple, but they only tend to appear when solar activity is really high. At these altitudes, it's a reaction with nitrogen that causes the aurora to be tinged with purple or blue, and most commonly are at the lower parts of the display. Let's take a look at some photographs that show that layering of colors. Notice here that the red tinge is up at the top. Remember, because the reds take very high energies, and they're up about 150 miles in altitude. The blues and purples are rare because these are from nitrogen atoms at lower levels and also take very strong storm activity. You can even see the color differentiation from the International Space Station, especially the greens and reds. Speaking of the International Space Station, here's a short collection of time-lapse videos taken from 250 miles up. Let's enjoy this for a second. Pretty amazing, isn't it? It's great. The astronauts enjoyed taking pictures and time lapse like that from orbit. So coming back down to Earth, what do we need to know? What do we need to do to prepare to see the aurora? Well, here are some tips for you. First question is there a solar storm strong enough to trigger a display? And is the KP index strong enough to reach your latitude? Remember, obviously, being the farther north you are, the better. And they're rarely going to appear below 46 degrees north latitude unless you've got an incredibly big display, big storm. You want to make sure that the skies are clear, of course, but humidity can cause some horizon fog, so you need to watch out for that. The skies need to be clear and dark. Horizon glow from a nearby town, you don't want that in the northern part of the sky because it could be confused or even wash out the aurora. And of course, because you need the darkest skies possible, you don't want a bright moon in the skies because it could wash out the aurora. The main thing is, even if you do look at some of these aurora forecast sites, remember, they don't necessarily tell you that there absolutely positively will be an aurora. I've sometimes seen aurora occur when there wasn't a prediction for them at all, and other times everyone got all excited about a big solar storm coming our way and we saw nothing. So there's just so many variables that are at play in the dynamics of the Earth's atmosphere and magnetic field. You just have to go out and try it. Just have to go out and take a look and be patient.
Mike, speaking of observing the aurora, we're having a lot of questions about if sounds can be produced by the aurora.
Sounds. You know, for the longest time, people were reporting that they could hear some faint hissing and popping and crackling from the aurora, but many times they were just brushed aside because the aurora are generated so high up, remember, above 50, 60 miles. And so to be able to hear anything from that altitude was considered impossible. But there is a mechanism that can trigger sounds. And I've got a demonstration for you coming up here in just a minute about that. So we'll make sure that you can get access to this video so you can get these sites written down if you like. But remember, the best way is to actually go and look. So if you're not at a latitude that is conducive to seeing aurora, you might want to check out some of the webcam sites. On this webpage, you'll find a nice list of webcams for watching the aurora live. When you click on it, you'll get a list that looks like this. These sites will refresh photos anywhere from a few seconds to a few minutes, but there are some doing actual streaming aurora. And I was just looking at this site just before we started. This is from way up in northern Finland in a region called Lapland. And let me take a second and let's click to that site right now and see what is going on. So this is a live look. There were some clouds about an hour ago. There were actually just some faint aurora. Now, I don't know how easily you'll be able to see, but there are some stars. There's the W of Cassiopeia right there. And there is just a faint hint of green here, and maybe even what looks like a pillar. So there's just a little bit of a hint of aurora going on there right now. Their forecast tonight was actually for partly cloudy skies, maybe a little snow later, but there is just a hint right there, right now. So this is from Lapland in northern Finland. There's another site as well that, let's see if we can find that one. This one I was looking for, so it will go live in about 20 minutes. This is from Yellowknife in the Northwest Territories up in northern Canada. And so as you can see here, they have a nice all sky camera that refreshes on a pretty frequent rate. So be sure to check that list. If you're nowhere where you can see the aurora from your latitude, these can be some pretty fun ways of streaming things in live and seeing what's going on. And since these are so far north, you have a much better chance of seeing them, even if it's not a major storm, because there's solar wind going on all the time at that location. All right, let's go back. One of the questions that we get a lot is, is there a best time of night or even a best time of year to look for the aurora? Well, by far the largest factor is whether a major solar eruption is taking place. After a major solar flare, 24 to 48 hours later is when our chances increase of seeing northern lights. But during the times of normal baseline activity, it does seem as though spring and fall tend to have a few more displays on average. It wasn't until recently that we learned why that is. Turns out the orientation of the Earth's poles relative to the sun at spring and fall tends to allow more particles to enter the Earth's magnetic polar cusps. As for the time of night, during a major geomagnetic storm, you can look anytime it's dark, but on average, it seems like the best times range between about 11 p.m. and 2 a.m. Let's get back to that question. Can you hear the aurora? Well, some observers, particularly that were underneath the auroral oval, have reported faint sounds of hissing and crackling during auroral displays. But like I said, since most of the aurora are occurring above 50 miles, it should be impossible to hear static from that high. And so many reports were put aside as imaginary thinking. But more recently, with sensitive equipment, sounds actually have been recorded. So what's going on? Now, these might be kind of hard to hear. What you're hearing are greatly amplified, taken from underneath the auroral oval. It turns out, while the sounds are connected to the aurora, they aren't generated up at the source. They are sparks of electricity discharging beneath the aurora in an inversion layer of the atmosphere. A temperature inversion is where a blanket of relatively warm air traps cold air next to the ground in calm conditions. The sounds are caused by the buildup of electrical charges in the inversion layer, usually only about 75 meters or 250 feet up. The more intense the aurora, the more active the electrical discharges in the inversion layer, and the more audible the sounds will be. So yeah, it was only in recent years that scientists were able to figure out where those sounds were actually triggered. So they're actually much closer to the ground, but they are triggered by the aurora themselves. I've got one more atmospheric feature to show you, and it carries the nickname Steve. Unlike traditional aurora, these are ribbon-like displays that usually run from east to west, not down low in the north. They were long thought to be a type of aurora. They've been observed since the 1700s, but they aren't aurora. In 2017, aurora watchers in Alberta, Canada studied them and proposed a different explanation. They're generated in the atmosphere, but through a different process. By analyzing satellite data, these ribbons are caused by a 15-mile wide band of hot gases at an altitude of 280 miles. They could be a flood of high-energy electrons flooding down into the ionosphere, which are usually absent in that region. The friction with the atmosphere superheats the air molecules to thousands of degrees, and the electrons are blown out. That's called a plasma. The term Steve, yeah, where did that come from? That originated from a photographer. His name is Chris Ratzlaff, who suggested the name Steve from the animated movie Over the Hedge, in which its characters chose that name for something unknown. Well, of course, with a new understanding of the physics behind it, the name Steve now has been given an acronym. It stands for, you ready for this? Strong Thermal Emission Velocity Enhancement. Say that really fast. Kind of reminds me of NASA. I mean, they have acronyms for just about everything. This shot here was actually shot right here in Michigan from Port Crescent State Park by Axel Mellinger. That's up near the Michigan Thumb. And we saw it. It was clear. The green was hard to notice except in the photographs, but it was very obvious. So there's another atmospheric phenomena that might look and feel like the aurora, but they're generated slightly differently. I want to acknowledge the fine photography and video that was shared in the program. If you'd like to review this list and the other websites listed during the talk, you can view a recording of this program on our Facebook page and next week on the YouTube channel, the Delta Planetarium YouTube page. And here are the links to our website, YouTube, and Facebook pages. In fact, please subscribe to our YouTube channel because there are lots of other presentations like these. And in fact, a special one on the series about constellations. So I want to thank you all very much for joining us. Be sure to check those links and happy aurora hunting.